Okay, welcome to Jamie Robbins. And Jamie and I have known each other for a long time through our mutual friend, Larry Wasserman. And although we don't work in the same field, we both work in statistics to some extent, but I always find with Jamie, it's very interesting talking to him and a lot of fun to have him around. We've had some fun times together. But since I don't know a lot about causal inference, I brought in my local expert, Stefan, who's also my son-in-law. And we'll have a chat. So, Jamie, I'm going to just start sort of a high level. I understand your background is not traditional, I guess, and as a statistical researcher. Maybe tell the students and everyone sort of a little bit about how you started off in epidemiology, statistics, and eventually causal inference.
Okay, well, I went to college, and then I dropped out without a degree. I went to medical school and I got an MD degree and was practicing medicine. That's my only post-high school degree. And I was a political activist. I started working with trade unions who when they get sick at work, they go to the company doctor who'd always tell them it was smoking. And so my friend Mark Cohen and I started an occupational health clinic. I would see patients in the clinic. I would have to decide what was wrong with them and then testify in court cases whether the cause of their illness was, in fact, their exposure. And from that, I got interested in how you tell whether something causes something else. So I took a few courses at sort of basic courses at the Yale School of Public Health while I was in this occupational health clinic, and I got interested in methods for figuring out what causes what.
Did you get a degree in epidemiology?
Nope.
So your only degree is an MD. Did you have a math background before all this?
Yeah, I was a math major in college.
Oh, good. Okay. As far as the paper is concerned, so we originally thought we'd cover, choosing one paper might be the 1986 paper on the G formula. And that paper is quite difficult. So I guess you and Stefan agree that maybe the paper, what year is the paper we're going to talk about?
The 1999 is not this paper.
So right. That's the paper we'll talk about. So Stefan, do you want to start by some questions or? Yeah, go ahead.
So when I wrote the 1986 paper, I had never talked to any statistician or anything, so I made it all up on my own. So it's very complicated because I was trying to be very general and I had no idea what the rules of the road were, sort of.
Well, certainly where it was enough notation in the paper, the first 2 or 3 pages.
So, okay, so your 1999 paper, it's about marginal structural models. Just kind of to get everyone oriented, can you tell us a little bit about how you see marginal structural models in the context of your broader work?
Okay. I think the easiest way to see it, not necessarily the way I totally saw it right at the start when I first thought about them, was suppose I ran a randomized trial with, for the moment, time fixed regimes, like, take continuous treatment, or it was one arm, don't take any treatment was another arm, take treatment every other day, and so forth. And if I told you that was a pure randomized trial, then association is causation. In any of your favorite models, from least squares, if you want to adjust, you could regress. Let's say I'm interested in a outcome at the end. I could just regress y on some summary of your treatment history, and that would be causal if I got the model right. Okay. And I could do Cox proportional hazards model if it was failure time, any model so those are causal. Okay, so I asked the question, well, now you didn't randomize up front. People come back each time and you look at their past history and decide on a probability that you'll treat them at this time. And that's my data set. So in fact, we use observational data, but mathematically, it's such a design is just a design without unmeasured confounders, which we generally assume, except for sensitivity analysis, and where you know the randomization probabilities because you designed it. In observational study, you have to estimate the randomization probabilities. So let's stick to the sequential randomized trial. I want to ask the same questions I asked when I randomized up front. And at least in 1986, no one knew how to do that in the epidemiology and statistical literature. I won't say in operations research and Markov decision literature, they didn't, but I'd never heard of those literature. So I first figured out this thing of the G formula, which is sort of, but another way to estimate the same thing is through marginal structural models and inverse probability of treatment weighting. And once you give each person a weight of 1 over their probability of the treatment, they did indeed get, that's in quotes, it's you multiply the probabilities of treatment at time m given the past. Once you do that, and there's no confounding by unmeasured variables, my past is the time-dependent covariates, and past treatment. Once I divide by that product of probabilities, I now, inside the computer where I've weighted people, actually have a trial where you can think of, I gave everybody any regime up front. So you just do the same analysis you did before, but by weighted least squares, and you're analyzing that data as if everybody had randomized up front. Association was causation, because that weighting keeps the time-dependent, makes the time-dependent covariates no longer predict future treatment given past treatment. So you can just pretend they're not there when fitting the marginal structural model, but you had to use them to get the weights rather than adjusting for them in the regression model itself, which leads to bias. So anything you could say about a normal model, you can say about a marginal structural model, because I'm doing the same thing you would do in a randomized trial where everything was randomized up front and associations causation.
Well, I'm sorry, how does this sync with time-dependent covariates in the Cox survival model? Like, they're used a lot. Does this
no problem.
change? Is it this? Does it give you the same kind of analysis, or is it?
Yeah, so it depends. Okay, so suppose you were running a randomized trial up front where you were going to use the Cox proportional hazard model.
Yeah.
You may have measured a lot of time-dependent covariates. Well, what you do is you essentially throw them away. You can actually use them to get more efficiency, but let's forget that because that's so you throw them away and you just do regress. But I have time-dependent exposures, right? Some people took it every other day. Some people took it every day. There's all sorts of regimes people are following. You can think of there are many, many, many arms, okay? So they're all regimes. And all I do is I do a time-dependent Cox proportional hazard model. I wanted the hazard ratio given your past treatment history. And that is now the causal hazard ratio. It's the hazard ratio that you see when you've randomized a bunch of regimes. It's a kind of association, that's causation. So that's what I want to do. The time-dependent covariates are relevant. Unfortunately, in my data, things weren't randomized up front. In fact, treatment choice was based on past time-dependent covariates and possibly past treatment. So I want to reconstruct the trial I did up front, the one where associations is causation, because I randomize them without regard to the L's, and all I do is divide by the probability of your treatment each time given your past covariates and treatment. And that makes copies of you. You know, if your weight's 10, there are 10 copies of you. And then I analyze it with a normal Cox model, but viewed as a statistical procedure that's just Cox model, a weighted Cox model with the weights being what I was just discussing.
So in the paper, going to the paper itself, there are kind of three ingredients that are very important to getting the final result. And what you call them in the paper is first kind of your original theory from the 1986, 1987 papers. That's kind of the sequential version of the potential outcomes model. Then you talk about this assumption of essentially sequential randomization or sequential unconfoundedness. And then you write down a marginal structural model, which kind of specifies, in this case, a linear relationship between the cumulative exposure and potential outcomes. So in setting this up, you called the first thing a theory, the second an assumption, and the third a model. I was wondering if you have kind of how you think about these terms and kind of why you chose to use one sometimes and another place.
Okay, so I'm not, sometimes I have real good reasons, sometimes I don't. So I sometimes call the first one the counterfactuals model, where you have, you know, time-dependent covariates, outcomes, feedback, you know, anything else going on. I sometimes call that a causal model now, rather than a causal theory, because I was comparing it at that time to what people were doing with directed acyclic graphs, Pearl and Glymour, Spiritus and Shines. Theirs was not a model in any sense. Theirs was a theory of how to do causal inference. So I thought, well, in this, since I'm talking about that, it makes more sense to call it that the theory, the first part. The second part I call an assumption because it's not testable. That is, because it says there's no unmeasured variable that's a common cause of both treatment and the outcome, and you don't have data on the unmeasured variable, you can't know that it's true. You can know that when they say in the sequential randomized trial, where I really, each time people came back to me, I flipped a coin based on what I could see, not based on their use. I do know it's true, because to be a confounder, you have to be a common cause of the treatment and the outcome, and the causes of treatment were that coin that was only, its probability only depended on the observed past. So it's always, so 2 is not an assumption in a sequential randomized experiment, but it is an observational study, because in a sequential randomized experiment, you only know it's true because you designed and the actions you took. The data, if I just gave you the data and I don't tell you whether it's from a sequential randomized trial, an observational study, you have no idea. You'll say, I don't know whether that's true or not, because I don't know whether it's a sequential randomized trial. Since I tell you it's a sequential randomized trial, you say, yes, that assumption has to be true.
Thanks, that makes sense. And on a related note, after you introduced the linear structure for the marginal structural model, you also have a comment, and people often make comments like this in statistics, that, well, in reality, we don't really believe that this linear structure holds exactly, but we think it holds, it's a useful approximation. In the case, just a basic prediction, I want to predict y from x. This kind of result is very familiar, and we know that kind of if you assume linearity, but you don't actually have linearity, you find a best linear projection. I was wondering, kind of, do results like this also hold in the case of marginal structural models under sequential unconfoundedness, and kind of what the results look like in that case?
So first, I just put a simple model there because I wanted to explain what the method was to a general audience, including philosophers, because this is in a philosophy journal. In general, I would make a model as complicated as the data would withstand, so, these days you might use machine learning to fit the regret, it's just as if you had, okay, So there was nothing, it was only didactic that I made it linear in any way. If you look, I write it as it could be an arbitrary function of your A history. I write, and then I pick the arbitrary function to be simple. Now, in terms of what does it mean if the model's misspecified, luckily, what I've said before tells you, because it tells you if you had randomized up front and you fit a model that was misspecified, you're just doing association. So that's a prediction. That's a projection of your true regression model. Because in the weighted, inverse weighted world, I'm just fitting regression because association is causation. So however your projection does, same for me. It just has, if I know the undependent covariance of weighted, it just has, the regression function has a causal interpretation. And it's a projection of the causal regression function on what, you know, on the space spanned by the linear space spanned by, if it's linear, by the covariance you used. So the only causal thing to be worried about is in just prediction. You say, oh, it's a pretty good predictor because it got close to Y. But in the causal thing, you actually care about the coefficients, especially their sign, because you don't want to give someone a treatment that you think helps them but really kills them. And as we know, projections can change, get the signs wrong for some things. So it makes it much more important for you to try to, do the best you can to actually estimate the regression, I would say.
So
The non-metric regression. In other words, the mean of Y given various treatment histories.
yeah. So in the connection you make here, right, that kind of the weighting in when fitting the marginal structural model kind of lets you recover the regression coefficient or otherwise fit the model in kind of this ideal randomized trial. That makes a lot of sense. Are there settings where kind of there are different, more uniform randomized type trials you could run, and like one of them would give you a very different kind of in the randomized trial, one of them would give you a different linear regression coefficient than the other one? And it's kind of
two different, I'm not sure what you're asking. It's the same population or two different populations?
Two different populations. But I mean, I could imagine that I have one randomized trial where kind of I give people between 8 and 10 doses. And then I could fit the linear regression coefficient under the randomization. And then there's the observational study version of this. And the IPW weighting you use for marginal structural models gives you the correct coefficient for the randomized trial. But I could also imagine that there's another randomized trial where kind of people give much lower doses and you get a different slope, right? This kind of thing always happens with linear approximation. What I was wondering is, when you use marginal structural models, is this an issue that often comes up that kind of?
Well, it may not, but it should if people were being careful, because it's if it's the same population. So let's say I split the population randomly into one. I ran an upfront randomized trial, and so of one of the dose regimes you said, and the other randomized trial with smaller doses or different times, and they gave different answers. Well, they will give different answers non-parametrically. By definition, you'll say, well, in the one trial, I can estimate the things that are identified are the regimes people had. That's called the positivity assumption in causal inference. So basically what you're saying is non-parametrically, I only have positivity for certain regimes in one of the randomized trials, and for other regimes in the other randomized trials. And if I don't make a model, a low-dimensional model, extrapolating without any data, like a linear model, then I have to say, then I can say I'm estimating the effects of both regimes and all regimes and whatever I want. But all I really can do is estimate the regimes that actually happened in the data here and there, and they may differ completely. And so the goal you're trying to always do is to estimate what you can from the data, what you couldn't non-parametrically identify. And then when you try to go further than that, you are modeling in the sense that you're a priori saying, here's a lower dimensional version of reality that I have no idea whether it's true because I have no real structure known to me other than the non-parametric dependence of the mean of y on past A.
Well, so maybe sort of stepping back a bit. I mean, for someone like myself who's not a specialist in this area, I imagine for students, the area looks kind of daunting. I mean, and for an applied person who's faced with this kinds of problem, also a graduate student is thinking, I wonder if I should do my research in this area. It's a little bit scary. Seems like a lot of people first of all, working in the area, and not just in statistics, maybe more so in econometrics and computer science. And it also looks really difficult. So, I mean, do you agree with that? And do you think the work's it's gelled to a point where it's more accessible to practitioners?
Okay, there were a lot of things there. So I think there's been a huge advance in the field. Is it complicated? Yeah, it's complicated, but so is what you do for someone like me who doesn't do it. So I don't know how to measure the complication. You know, maybe I would flunk your course and you'd flunk mine, and we should never, no, but so that's one. The other thing is when I wrote these first papers, I usually had 10 references, 5 to the whole literature that I knew in statistics and epidemiology. Now there are, I would say, probably thousands of people now doing causal inference. It's the hottest topic there is, and there was more to be done because every, day on the archive there are many clever new ideas. Even though, of course, before they came up with them, I thought I had all the ideas figured out. But I was, no, I'm not kidding. But I was nowhere near right, and sitting to your right is someone who often has good ideas about this that I had no idea about. But I think it's one of the hardest fields now of all to keep up with because it's got so many things going on in it and so many smart people coming up with new ideas every day.
Well, related to that, is software at a point where it's stable and accessible to people?
Yes, for certain analyses. So the kinds of things I'm talking about, yes, but not the most advanced software that would be doing these highly multiply robust estimation when you don't know the treatment probabilities. Some people have some software that does that now. I know Mark Van der Land's group does, but how well it actually performs, I don't know. The people I work with in the causal lab at Harvard, they're still mainly doing the non-multiply robust, non-double robust things, even though we've had software that does the others. I don't think it's just been vetted enough quite yet. So, and for all the other techniques, I think, it's probably as usual, I think people write their methods before they get good packages. And so there's some delay. And so probably depends on how long ago the methods were published.
I think I was going to ask, it seems that the senior thought leaders in the field, yourself being one of them, reportedly have not got along so well. It seems like there's been, not a lot of harmonious work. I mean, people doing maybe very related work, but not cooperating. Is that your feeling? If it's gotten better?
Well, one good thing is we've gotten older, so none of the, I would say, at least in statistics, the three of us who are most, Pearl, Ruben, and I, we're not the leaders anymore. We're just the old, the old guys. So it doesn't really matter, luckily, anymore whether we get along or not. And which is nice because it did matter once. Their personality conflicts. I have a well-known one with Don Rubin. I have a lot of good reasons for feeling that way.
You're such a laid-back guy. It's hard to imagine.
Today, Pearl's much more complicated. He's a great person, and I really like him. And he's, really brilliant. His stuff is fantastic. But in published work, he tends to toot his own horn in a way that's not always pleasant for somebody else who's working close to him. But at a personal level, I like him a lot.
So are you still hard at work in this field, or are you starting to slow down and enjoy life more?
I'm starting to slow down. It's not, they usually say enjoy life more, but a lot of reason to slow down is your brain has slowed down. I'm not who I was 20 years ago. I can't keep the whole thing, keep up, but I still am working and stuff, but yeah, I spend a lot more time bicycling. I don't read the literature carefully, I'm not, the people I trained and the people you trained and so forth, they're the leaders now who are doing all that. I mean, it's just, for me, age and loss of both interest and speed.
Well, maybe that's a good time to wrap up, but it's been a lot of fun, Jamie. Thank you.
Thanks for doing this and having me.
Hope to see you soon. If you still go to you still go to any of our annual meetings, or
I go on uncertainty and artificial intelligence in Barcelona in 2 weeks.
sounds nice. Okay, so I'm going to